because we still have to do 2D forces, which we haven't really touched on yet. I don't want to do that at all in the next exam because it's kind of complicated and I feel like it's a difficult topic to cover in just a day and a half or so. So we'll not have two-dimensional forces in the next exam, but we are going to have friction. We are going to get into friction. So we're going to be sort of skipping around a little bit in the next day and on Monday. But just to give you a heads up, we do have an exam on Wednesday, 1 week from today, and we're not having class on Friday. So we're going to cover a couple of new things today, and then we'll do some more practice on that in the class on Monday, and then we will have some review time on Monday too of these questions. We will have projectile motion. As you're studying, make sure that you really have on projectile motion. Make sure that you're able to solve a system of equations and or solve a quadratic equation like we did in class. Look at those supplemental problems that we did in class. Look at the homework problem that we did in class. If you look back at the old tests, you'll see a bunch of, you'll see some questions that have a function in IJK notation. Your problems are going to be more like word problems, like the ones that we've been doing in class, the supplemental problems that we've been doing, the homework problems. So I would focus more on those. You won't see a problem like, let me just show you an example. You won't see a problem like, let's see, I think there was one on last year's exam. What's exam one? Well, let's see. You're not going to see a problem like this. This is number 8 on fall 13 exam, where I give you a function. Here I've given you a function, 3.4 ti, 4.2 t minus 1.9 t squared j, and then I ask you to solve various things about that motion. You can do this, you have the ability to do this, but we haven't done it that much in class, so you're not going to see this. You'll see more typical like our word problems like we've been doing, where you have, something that's traveling in a certain path and you have to find the velocity or position at particular times. But if you look at these problems, they're probably fruitful for you to look at, but I wouldn't sweat them too much. You will have to, in the projectile motion, probably anyway, draw the position or velocity versus time graphs and calculate various things. Let's pick up where we left off. As I said, we're going to come back to the 2D problems. So let's pick up on page 104. In the United States, the unit of force, or the SI unit for the force, we've been using it, but it is the Newton. We abbreviate this as 1 capital N. The reason we capitalize that unit and we don't capitalize other units is because it's a person's name. So whenever you're dealing with somebody's name, you always capitalize the abbreviation, but don't capitalize it when you write it out, unless you're actually writing that person's name. Just a little bit of trivia for you. Be able to break these units down increasingly in the next few chapters, or in the rest of the year really. We'll be dealing with units that are built upon other units like the Newton, and so you need to be able to break these down into their basic SI units. The basic SI units for this are 1 kilogram meter per second squared. I wouldn't try memorizing that. Instead, we look at Newton's second law, which is F equals ma. I know the units for this are the Newton, the units for this are the kilogram, and the units for this are the meter per second squared. And so this is where we get this. And likewise, on future exams, we'll see stuff like this again, where I'll ask you for the basic SI units. For a particular unit, the watt, joule, other things that we'll encounter in coming chapters. And that's the way that you find it. You just look at the formula and break it down into its basic SI units. In the United States, the unit for force is the pound. You won't see the pound on the exam. We'll use all newtons, but just for reference, the unit for the force is the pound. And in newtons, just to give you some reference, I weigh about 700 newtons. Typical person weighs about 700 newtons. A small apple is about 1 newton. It's about 1/4 of a pound, like an apple, or like a quarter pounder from McDonald's. And I always tell my students that you should, when you go into McDonald's, if you eat at McDonald's, go in there and you want to know, when you want to ask for a 1/4 pounder burger, what should you ask for instead? A newton, not a newton pounder, but just a newton burger, because that would be about the same. And then see what the cashier says to you. Say, I want a newton burger instead of a 1/4 pounder burger. And then you would be cool, right? Okay. Does anybody know the British unit for mass, by the way? Right, and we use pounds, and often we'll use pounds to talk about mass in the British system, but that's not really correct. What is the British unit for mass in that system? No, it's not a stone. Somebody else said that yesterday. It's the slug. The stone might be something. I'm not sure what the stone is exactly. I tried looking it up. I couldn't find it. But it is the slug, is the British unit for mass. Again, you don't need to know about those British units. That's just sort of for reference. Let's try this quick test. We're not going to do this one, but let's try this other one. All right, true or false? It is possible to have motion without a force. It is possible to have motion without a force. So this statement is saying that you can have no forces acting on the object and it can still be in motion. Is that a true or is that a false statement? It is possible to have motion without a force. All right, I'm going to stop at 45. Okay, it is possible to have motion without a force. You can go back to Newton's first law that an object will continue in its state of motion, whether it's at rest or in motion, unless a force acts upon it. So that means that you can have something that's moving at a constant speed or a constant velocity and have no forces acting upon it. In fact, it will move at that constant velocity until a force acts upon it. So the answer here is A, it's true. We're going to skip this second one. It doesn't really it makes sense, but we're not going to. It's a little confusing. Okay, so we are going to skip this section because we're going to come back to this section later, I think even next semester, when we're talking about fields. And so I intended to take it out, but we're just going to skip the gravitational force in terms of Newton's universal law of gravitation, because we'll come back to this in much greater detail as we learn more about fields in the second semester. So I'm sorry to even have it here. We're going to skip all of this, the next 2 pages, completely. And actually the 3rd page, because as I said, we'll come back to that completely in next semester. So I'm sorry if you're not taking next semester, but we're going to spend so much time. You're just going to be sick of fields and gravitational forces and all that business. If you'll be sick of them, you'll be further enriched by your knowledge of gravitational forces. But not today. We're going to skip that. Now let's move right on to Newton's 3rd law. So just to recap, we have Newton's 1st law, which is often called the law of, what's it called? The law of inertia. The law of inertia, remember, inertia is a measure of a material that's dependent upon its mass. The mass measures inertia, that describes how easily it moves. So an object with a lot of inertia doesn't move very easily. An object with not very much inertia moves more easily. So it's difficult to move this disk because it has a lot of mass. It's difficult to move for other reasons too. But if you just had it out in space, it would be difficult to move just because it has a lot of mass. But it's difficult to move something smaller, like, you know, an ant or whatever, because it has a small amount of mass. The second law, which is called the law of, not everybody at once. We had the law of inertia, and then the law of, do you recall? No, it was the law of acceleration, and that was the whole, it was really an equation that F is equal to ma. That if I apply a force to an object, then I create an acceleration. The third law is sometimes called the law of reaction, or the law of action-reaction. I'm going to call it action-reaction. And it says that if objects 1 and 2 interact, then the force exerted by object 1 on object 2 is equal in magnitude, but opposite in direction to F21. And so, for example, if I have one object and I have another object, I'll call this object 1, this object 2. Object 1 is exerting a force on object 2, and we'll call that F12. And in a similar way, object 2 is exerting a force on object 1, and we'll call that F21. And so what this law is saying is that F12 is equal to the negative of F21. Right? The result of this law, and this is kind of mind-blowing, if you tell your friends this, they might say, no, that can't be the case. But it is true nonetheless. The result of this law is that no isolated force exists. There is no force anywhere in the universe in which there is not an equal and opposite force. So no isolated force exists. You will always, if you have one force, you'll have another force. Now, what type of force is this? When I have two objects that are touching, we had a particular name for that force. Do you recall? Wear them on your eyes sometimes. You have certain sports. This is a contact force because it requires contact between two objects. We had another type of force, which is called a field force. So that field force, if let's say that I'm not touching the surface of the Earth, like I jump up from the surface of the Earth and I'm, momentarily airborne, there is a force acting on me that is equal to our force weight. I don't know if we have talked about force weight already. That force weight is equal to the mass times the acceleration due to gravity. In the previous section that we skipped, we actually derived by g, and we'll do that later in the second semester. But our force weight is equal to the mass times gravity. So is this an isolated force, or is there an a reaction force that is equal and opposite to this force? It doesn't seem like there's another force, does there? Or does there? Is there another force that is acting here? When the observer law would say, yes, there has to be another force. So if you imagine, I'm standing here and the Earth is pulling down on me with approximately what? How many newtons? 700 newtons. So I have a weight of 700 newtons. 700 newtons. I'm also pulling back on the Earth with another 700 newtons. That's a bad spot. I'm also pulling back with a force of about 7. Pulling back with a force of 700 newtons. So the Earth is pulling down on me, and like I'm pulling back up on the Earth with the same force. Okay? Now, the Earth is so massive that force that I apply to the Earth is minuscule, right? Because the Earth has a much larger mass than me, so I'm not going to cause it to accelerate in the same way that it causes me to accelerate, because it's so much more massive. You follow me on this? All right, so I do have a reaction force in this case. That reaction force is me pulling up on the Earth. And while
my weight is 700 newtons, my reaction force is also 700 newtons. So field forces and contact forces obey Newton's third law. They always do. And the result of this contact force obeying is something we call the normal force. It'll be pretty important when we get into friction and the inclined plane, and well, we always have it. So the normal force, normal is a mathematical term. It doesn't mean like usual or regular, but in mathematics it means what? What does normal mean in mathematics? Oh, it's like a Friday, isn't it? What does normal mean? You recall from geometry? Give you a hint. It means perpendicular. So normal is a mathematical term that means perpendicular. The normal force is always perpendicular to the surface. Imagine I have an object that sits on a surface. I have two forces that are acting on this. I have the weight, Fw, and then I also have an equal and opposite force that is the normal force. This normal force is the table pushing back on the block. It doesn't have to be vertical. Normal does not mean vertical. I can also have normal forces that are in all different directions. See, I think I have a slide on the next page. Oh, so in this case, if I have this table, I'm just going to redraw it here, where the weight is pushing down, the normal force is pushing up. Let's imagine that the mass of this block is, I don't know, 20 kilograms. That means that the weight is equal to 200 newtons, because Fw is equal to m times g. 20 times 10 is 200. I can write my net force. I can say that the sum of the forces is equal to Fn minus Fw, and that's equal to the mass times the acceleration. In this case, the acceleration is 0, so I can say that Fn is equal to Fw. So in this case, we can calculate the normal force, and it's equal to 200 newtons. The normal force, however, isn't always equal to the weight of the object, and we'll see some cases where that's not the case, where it's not equal to the weight of the object. We'll work the problem today, actually. I can change the normal force in a couple of different ways. Like, for example, in this case, how could I change the normal force? I have this object. It's sitting on a surface. Say this is about, I don't know, it's about a kilogram or a couple kilograms. So it has a weight of about 20 newtons. How can I change the normal force? Right now, the normal force on this object is 20 newtons. How can I change the normal force on this object? I could put it on an angle, right? I could lift it. We're not going to get into do this, and that changes the normal force. That's good, but we're not getting into that just yet. A simpler way to change the normal force. Or what? I could push on it. If I push on this thing, then that increases the downward force. It adds a third force here of me pushing on the thing. So if I have an additional force here, then that increases the normal force. So let's say, for example, that I add a weight, I push with F equal to 10 newtons, then that means that my normal force will equal to, well, let's do the whole thing. We say the sum of the forces equals Fn minus Fw minus F. That's equal to 0. So my normal force is equal to Fw plus F, which would be 200 newtons plus 10 newtons, or 210 newtons. Okay? So I can increase my normal force just by pushing down like this, or increasing the mass of the object. I can also decrease it, as Dustin said, and we'll get into that. We're not doing 2D problems just yet, but I can decrease it. Well, actually, there is a simple way I can decrease this normal force. I can push down on it. What's another way I can decrease the normal force on this object? I can pull up a little bit. Pull up so that it's still touching, but that it, it has a force pulling up. Your scale, your bathroom scale, it measures not your weight, but it measures a normal force. Your weight is actually kind of difficult to measure, but you can, if you stand on a scale, you push down with the weight, and the scale pushes back on you, and it measures that as your normal force. Now, if you're standing perfectly vertically, then your normal force is your weight, and so it does give you your weight, but it's secondary. It's actually measuring the normal force. Okay? You could actually, if you hang on to something and pull up slightly, you'll get a lower reading on the scale. You ever done that before? I don't know why you would, but if you wanted to, you could do that. Okay, so also the normal force isn't always perpendicular to the normal force is always perpendicular to the surface. So for example, we can have a couple of examples of this. Like if I have an inclined plane, and again, we're not doing inclined planes just yet, but if I have an inclined plane, my normal force is always perpendicular to the surface. Not necessarily vertical. It can also be horizontal. Let's say that I have an object and I'm pushing with a certain force to hold that object on the wall, then the normal force in this case looks like that. So if I have this object and I want to hold it on the wall, I'm going to have to put it up like this and hold. I'm pushing against the wall on this object, and so the wall is pushing back with an equal and opposite force. So the normal force is often going to be perpendicular. It's often going to be vertical because our forces will be acting in a vertical direction, but it doesn't have to be vertical. But it has to be perpendicular to the surface. Okay, we're going to skip this for now, but we will come back to it. And we're going to skip right on ahead to friction. And we're going to skip all this. We'll come back to it. So don't cross it out or anything. We're going to come back to it after the exam. Forces of friction. We can have friction in two different scenarios. We can have static and kinetic friction. I'm sorry, not static and kinetic, something different. We're going to get to that. We can have microscopic or macroscopic. This is actually pretty cool. They did this experiment where they measured the frictional force. They took two objects. They were kind of rough, like this. And they measure the frictional force in between those two objects. In lab, you're going to measure the frictional force next week, actually. They measure the frictional force between those two objects. And when they're rough, it's like the pieces of the object catch on the other pieces of the other object. Like two pieces of sandpaper coming together. The grit on the sandpaper, it physically catches one another. This is called macroscopic friction. And mostly that's what we deal with, is macroscopic friction, where the actual crags and the different surfaces will connect with the other surface and cause friction there or cause forces. So this is macroscopic. But what they found is that as they increased the smoothness of the surfaces, they made them smoother and smoother, sanding them down or whatever, however they make them smoother. And then they measure the frictional force between them. What would you expect to happen to the frictional force as you make those surfaces smoother and smoother? They get smaller and smaller. But what they found eventually is that they saw an uptick, that eventually the frictional force began to increase again. Now on this side, we have our macroscopic. On this side, we have our microscopic. Because what happened as those two surfaces got smoother and smoother, well, a couple of things happened. First, the surfaces, they just get closer and closer together. So they have a greater surface area touching. But something else happens that's fairly interesting, that as you make these surfaces smoother and smoother, is that they become in closer contact on the atomic or the molecular scale. So that charges on either side of them, negative and positive charges, will actually begin to get closer to one another, and then that causes the frictional forces, as they measure them, to increase. All right, we typically wouldn't call it friction, but it is a type of friction, but it's a microscopic, on a microscopic scale, that the charges in the materials are actually attracted to one another, and that increases the amount of friction. So this is microscopic friction. Okay, there are two types of friction that we'll deal with, and they are static and kinetic. Also, we need to understand that friction is almost always opposite the direction of motion. So if I'm trying to push this desk in that direction, the frictional force is going to oppose it in this direction. And there are very few cases where that's not true, that the frictional force will almost always oppose the direction of motion. All right, static friction acts on objects that are static, that are not moving. We use a lowercase script f to describe this, fs, and it is less than or equal to, static friction is less than or equal to something we call the coefficient of static friction times the normal force. This is the Greek letter mu. Mu. It looks like an M, but it's not an M. It's like a U that has a little tail on the left. So it's like a U here, and then it has a little tail. So if you want to draw an M, that's fine. That might confuse you with math. But this is the Greek letter mu. And then this, gosh, what is this force? This is our normal force. So our static friction is equal to the coefficient of static friction. Times the normal force. The coefficient of static friction is dependent upon the surfaces. And so if I have different surfaces, they'll have a different coefficient. So for example, if I have metal on ice, that's going to have a fairly low coefficient of static friction. But if I have rubber on asphalt, that's going to have a fairly high coefficient of static friction. All right, this is just dependent upon the surfaces. And then the normal force is just dependent upon your situation. We'll work through some problems like that. Then we also have kinetic friction. Kinetic friction, we're going to use a lowercase f with a k. It is equal to mu k times the normal force. Times the normal force. I'll explain why we have these two different things. On the static friction, notice I used an inequality. It was greater than or equal, or less than or equal to, and here I actually use an equal sign. I'll explain to you what that means. Kinetic friction acts on objects that are moving. Actually, let's go back and I'll explain that inequality to you. In static friction, we have this inequality because the static friction is not always the same. Imagine this desk. I'm pushing on this desk right now with a force of, I don't know, 10 newtons in that direction with about, 8 pounds or so. I'm pushing with, like 10 newtons is about 2.5 pounds. So I'm pushing with a force of 10 newtons. So why is it not moving? Why is the object not moving? I'm pushing a force in that direction, but the object's not moving. So why is it not moving? The friction is too big. So I push on it with 10 newtons, and so therefore my static frictional force must be equal to 10 newtons. Okay, well all I have to do then is just push with more than 10 newtons, and that'll make the desk move, right? If I exceed this static frictional force of 10 newtons, then I will make the desk move. Right now I have a net force equal to 0, and I need to increase that net force so that it's more than 0 to make it move. So now, you ready? I'm going to push with 15 newtons of force. Are you ready? It's going to go flying out the door. Okay, here we go. I think I'm actually pushing like 20 newtons of force. Pushing like as hard as I can on this thing. Why is it not moving? What has happened to the static friction? I push with a bigger force. I push with a force of, say, 20 newtons. Then why is it not moving? What has happened to my static frictional force? It has gotten bigger. So the static frictional force, as long as the object is stationary, will increase to meet whatever force you're applying to it. Okay, you'll see this and how it comes up in problems, but just keep that tucked away for right now. Another interesting thing about kinetic and static friction. Oh, and notice also that we don't have that inequality here, because once you get something moving, the kinetic friction doesn't really change. It's pretty much the same. At some point you change the material, and it will change for that, but for the most part, that kinetic friction doesn't change. There's something interesting that you can do to show that mu k is almost always bigger than mu s. For almost all materials, kinetic friction is less than static friction. You probably know this. If I push on this thing, it's really hard to get a big piece of furniture moving, but after I get it started, it's hard to get it started, but then after you get it started, it's pretty easy to keep it in motion. And the reason for that is that coefficient of kinetic friction is almost always bigger than the coefficient of static friction. So imagine I need a big force to put in motion. But then, after I get the object in motion, I just need a small force to keep in motion. Almost always, our static friction is bigger than our kinetic friction. You can try this when you leave today, when you leave campus. If you're driving up Maywood and you're at that stop sign up at Maywood at Highway 1, I ask you to do something that you might not do very often. But when you come to that stop sign, you should stop. Like, try stopping at the stop sign. Drive along, it's like, oh, my friend said I should stop at this stop sign, and something cool will happen, and stop very slowly. So put your feet on your brakes and come to a complete stop. Not like a rolling stop, but a complete stop. And what's going to happen, you might have seen this before, and just as you come to a stop, what happens to your car? Right, it sort of lurches forward just a little bit. The reason that it lurches forward is because there's a difference between the coefficient of kinetic friction and the coefficient of static friction. As your tires are rolling, you have these metal rotors inside your wheel, and then there are these two brake pads that clamp down onto it. As the tires are rolling, what is the type of friction between the brake pads and the rotor? That's kinetic friction, because the whole thing is moving. The tires are moving, the rotor is spinning, and the brake pads are sliding against it. What happens when it stops? What type of friction is at play? Static friction. And so there's a disconnect or a discontinuity between our kinetic friction and our static friction. All right, so consider a block on a table. What is the maximum force so that this block will remain stationary? So here I give you the mass of the object, I give you the coefficient of static friction, and I want to know what force can I apply to this without causing it to move. What is the maximum force I can push on this thing and it not move? Take a couple of minutes. What you're going to do is first you want to label everything that you know. You'll need to apply Newton's second law. Newton's second law says that the sum of the forces equals mass times acceleration. And then also Newton's second law will say separately that the sum of the forces in the x direction is equal to max, and the sum of the forces in the y direction is equal to may. So from Newton's second law, I can create two separate equations. And what I want to do is to figure out what is this force. This is a static problem, so the acceleration will be 0. You can see a problem something similar to this. When I say there will be no 2D forces, I mean there will be no forces that are in between the x or y axes. But in this case, I only have forces on the x-axis or on the y-axis, and none in between. You're going to set up two sets of equations. Sum of the forces in the y, sum of the forces in the x. What forces do I have in the y? Normal force and my weight. So you want to create an equation that deals with these two forces. Notice one is positive, one is negative. And then in a similar way, you have my force and my static frictional force, which are in the x direction. Also, you have one other equation that you know about forces, and that is that the static frictional force is less than or equal to, less than or equal to mu s times the normal force. All right, I'm going to start filling this in. All right, this is our normal force minus our weight. That's equal to 0. And this is going to be F minus Fs. That's equal to 0. Now look, I'm looking for this quantity. That's the one that I want to know. And I can look at this from this equation and say, well gosh, F is equal to Fs. So if I can figure out what Fs is, the static frictional force, then I can figure out this force. But I don't know this force. I need to figure out a plan to determine what is this static frictional force. How am I going to do that? Well, I know the static frictional force is equal to this mu times my normal force. All right, go with me on this? If it's equal to mu times the normal force, but I don't know the normal force, I can figure out my normal force over here, because I know it's related to this weight. And then I can come over and figure out what is my static frictional force, and then I'll have my answer. So my normal force is equal to what? It's equal to 10 newtons, because my normal force is equal to my force weight, which is equal to m times g, or 1 kilogram times 10 meters per second squared, and that's equal to 10 newtons. So that means I can figure out my static frictional force. I'm going to make this no longer an inequality but an equality, because I'm looking for the maximum static frictional force. It's equal to 0.1 times my normal force, which is 10 newtons, or that's equal to 1 newton. And then I know that this is equal to 1 Newton. So that's my answer there. Okay. May I go down from here? Let's do a few practice problems. We're going to skip this one. This one's going to be more for the next test. We'll spend a couple more days on these after that next test. We might get into them a little bit in the next class period, but they will not be on the test. Let's try this multiple choice problem. The dock worker loading crates on a ship, 100 kilogram crate requires a 400 Newton force to set it in motion, and after that a 300 Newton force to keep it in motion. What is the coefficient of kinetic friction between the crate and the floor? And I'm sort of all over the board here. Please share your answer with your neighbor. What you want to do here is figure out there are a couple of different forces in here. Figure out which of these is the kinetic frictional force. You'll also need to know what is the normal force, and then with that information you should be able to calculate your coefficient. All right, I'm going to stop at 235. Guess if you're not sure. Okay, let's see. I think A is right. I'm going to go ahead and mark it. Let's check it out. So which of these, is it the 400 or the 300 that is the kinetic frictional force? It's the 300 newtons because it's in motion. So I'll go ahead and list that. Fk is equal to 300 newtons. And I also know that this is going to equal to mu k times the normal force. And so now I need to know what is the normal force, and I can calculate what is this mu k. I have a 100 kilogram crate. It's 100 kilograms. That means that I have a weight, Fw, equal to m times g. That's equal to 1,000 newtons. So the force weight is 1,000. That means that I also have a normal force equal to 1,000 newtons. It doesn't always have to equal the weight, but in this case, because there are no other forces, and because it's on a horizontal surface, it is equal to 1,000. So I say 300 equals mu k times 1,000 newtons. And then so mu k is equal to 300 over 1,000, which is 0.3. There are no units on the coefficient, as you can tell just from the formula, because I have newtons on one side and newtons on the other side. The coefficient is unitless, has no units at all. It's always found experimentally. You'll determine it in lab. All you do is you measure the normal force and you measure the frictional force, and boom, you got your coefficient. So there's no fancy magic to it. You're just calculate, or you're measuring what that coefficient is. Okay, we're almost done. Let me give you a little guidance on what you can do over the weekend if you want to get ahead on this. Where all this stuff with inclined plane things, we're going to push that off to the next exam. But there's still quite a bit that you can do as far as homework. I would look at problem number 1, problem number 2. We've worked problems like both of those. Problem number 3 as well. I don't know that we worked exactly like that, but all you have are forces that are in different directions. Problem number 4, not problem number 5, we'll deal with that later, not problem number 6. Problem number 7, that's just like the multiple choice that we just did. Not 8. And problem number 9. I would particularly look at problem number 9 just because it's a little bit different than what we've done. And we'll look at some next time that are similar to it, but problem number 9, well, it'll be good for you to go ahead and look at over the weekend before we see something similar on Monday. Okay? Those first ones are pretty straightforward. They're a lot like what we've done, but problem number 9 you'll probably find a little challenging. You know, with the homework, what I recommend is that you try working through it all on your own, and then you can go back and look at the solutions and see where you messed up. Or if you look at it and you're completely lost, why don't you look at the solutions and then put them away and then go and try to work out the problems. And just make sure that you can do it without any help at all, that you understand the steps that you go through. In general, I recommend that also for the exams as well. And then also problem number 10 is similar. All right. Let's do a few clicker questions. We have a few minutes. I don't want to scare you too much. Actually, this test is easier than it could be if we added the inclined planes. But the projectile motion stuff, students find that difficult. And also Newton's laws, even just in one dimension, students find difficult. So you need to spend a little time practicing. That exam is coming up soon. It's right around the corner. Just one more class day. Where did we leave off on these? We did some of these, am I correct? See if I remember? 4.2. So this one? We did this one or we did not do it? The next one? This one? Okay, so what would be done to the cart in order to give it constant acceleration? What do you have to do to this cart that's traveling horizontally to travel with constant acceleration? You can think Newton's first law, Newton's second law. All right, we'll stop at 40 seconds. 40? Okay, awesome. C is right. In order to have it move with constant acceleration, I know that F equals ma. In order for that to move at constant acceleration, I have to have a constant force. Let's see, what happens to a frog's car when it breaks down? It's towed away. That was a funny joke. The 7:30 class. Don't y'all love 7:30 classes? Physics has always been at 7:30 for since time began here. All right, a very large truck sits on a frozen lake. Assume there is no friction between the tires and the ice. A fly suddenly smashes against the front window. What will happen to the truck? Think Newton's third law. Okay, at 35, we'll stop at 35. Just a couple more seconds. Okay, it would seem, we're assuming no friction between the tires and the ice. And so if we assume that, that's not really true. Actually, there is some friction between the tires and the ice. But if we assume that is true, then C is the right answer. It will, when the fly smashes into the front window, the truck will accelerate backwards. Now, I know what some of you are thinking, they put B, and that's not necessarily wrong. That after the fly smashes into the window and accelerates the truck, then the truck will move at a constant speed. So I understand what you're putting, but in the instant that the fly smashes against the front window, it will cause an acceleration both for the fly and for the truck, because there's an equal and opposite force being given on them. Let's do one more. Oh no, we'll stop at this. But hey, listen, I'm going to go ahead and post these online, because we only have one more class period. We're not going to be able to do all of these. I'll sort of take out the hardest ones and we'll do them in class. But I'm going to go ahead and post them on the concept test page on our website. You can go ahead and download them if you want to start looking at them over the weekend. And I recommend that you do so. We're not going to do them all in class. You have a great day. Have a good weekend. Have a good fall break.